Oh, we are going to learn the lesson 11.3 on the perimeters and areas of similar figures. Our goal is to compare the perimeters and areas of similar figures. Well, the truth is we've already talked about the perimeters of similar figures, and so it's a little bit of a review to state here that the ratio of the perimeters of similar figures is equal to the ratio of their sides. Actually, it's also equal to their scale factor, which we've talked about previously also. So the ratio of the perimeters of similar figures is equal to the ratio of their sides. It's just a good fact to know, but it can be a little confusing because now what we're going to do is talk about the ratio of their areas. So to start this, actually, I'm going to add a page and talk about a square because squares are pretty straightforward to talk about. And so what I'm going to do is have a little square drawn here. And let's actually, we need two squares that are similar. All squares would be similar because, yes, all squares would be similar. Sorry, I gotta clone this. All right, so, but just make it smaller. So let's make it about half the size. That'll work for us. But let's say that this one has sides of 3. Now it's a square, so all the sides would be 3. And let's say that this one over here then, double that, would have sides of 6. Because it looked like it was about double, and we're just doing this as an example. And so we've got squares that have sides of 3, a square that has a side lengths of 3, and another square that has side lengths of 6 units. Well, if we come over and find the perimeter of this first, well, actually, let's talk about the ratio of their sides. The ratio of the sides would be a 3 to 6 ratio, which reduces to 1 to 2, just twice as big, as we've kind of already talked about. So now we come to this first square and we find its perimeter. 3, well, it's a square, so actually we can use our little formula that we talked about previously here, just a little while ago, which is the number of sides times the length of one side. So there's 4, because it's a regular polygon. A square is a regular polygon. So we take 4 for the number of sides times 3, which is the length of one side, and so what you get is 12. The perimeter of my bigger square here would be n, number of sides, still 4, now times 6. 4 times 6 is 24. So now we talk about the ratio of the perimeters, and the ratio of the perimeters would be 12 to 24, but that also reduces to 1 to 2, which makes sense because, well, we've already previously talked about that and the fact that it would be the same as the ratio of their sides. But what we're really going to get into is area, ratio of their areas. So let's find the area of this square on the left here. Area is s squared. So we take 3 and we square it. And what we'll get is 9 square units. Okay. The area of the triangle, or the square on the right, let's go to the right of it, is area equals s squared. Now we have 6 squared, and 6 squared is 36 units squared. And so what is the ratio of the areas? Well, the ratio of the areas is going to be 9 units to 36 units, which we could just say 9 to 36, but that reduces to 1 to 4, not 1 to 2. Now, what is the relationship between a ratio of 1 to 2 and a ratio of 1 to 4? Well, we'll write this ratio look like a fraction, but a 1 to 2 ratio, if you square it, both the numerator and the denominator, what you get is 1 to 4. And the idea of this makes sense if you think about the units used. For the ratio of the sides and ratio of perimeters, well, the ratio doesn't have any units, but for the side length or perimeter, we have a unit that's in one dimension, so it's just unit. And for the area, we have a square unit, so it's a two-dimensional unit. So going back here, the notes is presented in theorem 11.5, and it states that the areas of similar polygons, if two polygons are similar with the length of corresponding sides being in the ratio of A to B, then the ratio of their areas is going to be in a ratio of a squared to b squared. And so again, we have this side length here. Side length here of quadrilateral 1 is a ratio of a to b. The area of quadrilateral 1 to quadrilateral 2 would be a squared to b squared. And that would be the relationship. Focusing mainly, though, again, there's also another little bonus thing here, is that they actually are similar. As you can see in the bottom right there, quadrilateral 1 would have to be similar to quadrilateral 2. Otherwise, there's really no relationship there talked about, because we're talking about similar polygons. So that is the main idea of this new section 11.3, and we just have 3 examples to do, and these examples are relatively short. So you can add those to your notes. I'm just going to look here. I know we're 6 minutes into this lesson. I said it would only take about 10 minutes to teach, but we'll see what goes on now. So the ratio of corresponding sides of 2 similar hexagons is 3 to 2. We need to find the ratio of their perimeters. Well, according to our notes already, there's no work that we really have to do. If you look at this, you're thinking, well, how am I going to find their perimeters? You don't even have to find their perimeters. Just realize that the ratio of the corresponding sides is 3 to 2. That means that the ratio of their perimeters would also be 3 to 2. Now, the ratio of their areas, according to what we just talked about, would not be in a ratio of 3 to 2, but it would be in a ratio of 3 squared to 2 squared, which would equal 9 to 4. So the ratio of their areas would be 9 to 4, and going back, the ratio of their perimeters was the same as the ratio of their sides, 3 to 2. That's all there is to it. Now what we're going to do is we're going to use this idea then to kind of find areas or find perimeters based off of ratios of their areas. And that's going to be example 2. Example 2, a rectangular tablecloth is 60 inches by 120 inches. A rectangular placemat made from the same cloth is going to be 12 inches by 24 inches and will cost $5. Compare the areas of the placemat and the tablecloth to find a reasonable cost for the tablecloth. So here's the deal. If you're talking about a cloth, a piece of clothing most likely, you're going to be charged for the area of that material. So what we really want to do is compare the areas, but we don't actually have to find the areas of these rectangular cloths. Because what we notice is going from the tablecloth, let's do a ratio of tablecloth to the placemat, doing a ratio of the tablecloth to the placemat, what we get for their sides, and you can pick either dimension, but let's just start with the first one, 60 inches to 12 inches, and then we would reduce that, and so what we get then is a ratio of, well, 6 goes into both, 6 goes into, actually 12 goes into both, so it's a ratio of 5 to 1. It's a 5 to 1 ratio. Or you could think of it this way, the tablecloth is 5 times longer or wider than the placemat. And that works too for the 24 to 120. If you take 24 times 5, you get 120. So it's 5 times longer. But see, now that's the ratio of their sides. We want to compare their areas. So if it's 5 times bigger by a side length, how would the areas compare? Well, the areas, according to our theorem we just talked about, we would want to square that ratio. 5 squared, so let's just see, this equals to 5 squared would be 25, and 1 squared is just 1. So it ends up that the area would be 25 times bigger. So we could maybe write that as a sentence here to kind of explain what's going on. The area of the tablecloth, which is one word, is 25 times more than the area of the placemat, which is one word. Okay, well, now we've compared their areas. Now let's find a reasonable cost. Well, if the cost is determined by the area, because for cloth needed, the area, and the placemat said the placemat costs $5, and we know that the tablecloth is going to have 25 times more area, we can say that, let's start the sentence a little bit different here. A reasonable cost for the tablecloth would be 25 times $5, or $125. And that does seem expensive for a tablecloth, but it's probably some really fancy cloth used for this tablecloth. Also, think of each placemat costing $5. That seems pretty pricey too for just a little piece of tablecloth that is 2 square feet of material only. There's a pretty big tablecloth too, if you think about it. It's 10 feet, 10 square feet of tablecloth. All right, so that is how example 2 goes. And now moving on, and I'm just gonna check the time real quick, and I guess we're already over 10 minutes, 11:30. But moving on now to example 3. This example says that a store sells trampolines that are all regular hexagons. One trampoline has a side length of about, they're just using approximation here, so we'll just use 4.5 feet, and an area of, again, approximation, 52.6 square feet. What is the area of a trampoline whose perimeter, and again, of the trampoline, they're all regular hexagons, whose perimeter is 67.5 feet. Now, at first glance, you may be thinking, oh, this is going to be like what we did in the previous section and finding area of regular hexagons, and that's going to be very cumbersome. But it really is not going to be, because what we just have to do is compare their side lengths and use that ratio to find the ratio of their areas. So let's kind of set this up. We've got, well, let's find, if we know the perimeter is 67.5 feet, let's find the side length. Now it's a regular hexagon, so all the sides are the same. So if the perimeter, let's use that formula we had previously. Perimeter equals n times s, the number of sides times the length of one side, which works for regular polygons. And we know that the perimeter is 67.5 feet, and the number of sides in a hexagon is 6. We can use this to find what the length of one side is. Divide both sides by 6, and what we find out is that it's going to be 11.25. So the side length is going to be 11.25 feet. Let's just double check that the math is correct on that. 67.5 divided by 6. See, 11.25 feet. So what we get then is we get a ratio. Our smaller, and we know it's smaller now because, 4.5 feet is less than 11.25 feet. Our smaller hexagon has a ratio, has 4.5 feet per side, and we're comparing that to our bigger hexagon, which will have 11.25 feet per side. So going small to big, I'm just gonna write small to big, and let's simplify this, our sides here. Let's just do our sides. I'm just gonna color coordinate things here. Our ratio of our sides is 4.5 feet to 11.25 feet. Well, let's get that into some whole numbers. What we could do is the feet cancel out in our ratio, so we have no unit in our ratio, and let's multiply both first by 4. So 4.5 times 4 is 18, and 11.25 times 4 is 45. 45, I almost wrote 44. And then let's reduce that by 9, so it's a 2 to 5 ratio. So the ratio from the smaller hexagon to the bigger, for their sides, or perimeters for that matter, would be a 2 to 5 ratio. Oh, I just thought of another thing we could have done. We could have taken the 4.5 that was right here and multiplied by 6, and actually got the perimeter of the smaller hexagon and compared those two numbers. But by comparing those two numbers, we would have also got our ratio of 2 to 5, which is what our sides ratio would be, our perimeters ratio would be, and technically then our scale factor, not technically, but would be, ratio, our scale factor would be 2/5. The smaller one was 2/5 the size of the bigger one if you're thinking scale factor, or vice versa, the bigger one is 5/2 the size of the smaller one, or 2.5 times bigger. That's what we're going with. But when we say 2.5 times bigger, we're just talking about a side length or the perimeter length, not area. So now what we want to do is find our ratio of our areas. So what we're going to do is square this. So we have 2 squared to 5 squared. So we have a 4 to 25 ratio. And now we're going to use that ratio to set up a proportion using the approximated area for the smaller hexagon, which is 52.6. So 52.6 square feet. So let's go small over big for our proportion. And so I'm going to put 4 over 25. That's the ratio we know for the areas, but the actual area, now I can't remember. Let's look up. 52.6. 52.6 was the, or square feet. Units are important here. 52 square feet was what the actual area of the bigger hexagon trampoline was. 52.6. So now, and what we want to find is the actual area of the bigger hexagon, so that's going to be our x. We'll just call that x for our variable. And so we cross multiply, so we get 4x equals, and then we get 25 times 52.6. And so let me just use my calculator here. 25 times 52.6, and I get 1,315. 1,315. And then we'll just divide by 4. Extend the page. Divide both sides. Oh, well, sorry, I forgot the unit on that. That would be square feet. Divide by 4. So x equals, and what we get then is 4 goes into 13 or 12 3 times, and then we got 11. 4 goes into that twice. We got 34. 4 goes into that, blanking here, but 8 times, and then we're left with a half. So let's just see here if I can do my math correctly. So we're just dividing by 4. 328.75. Yeah, messed that up. Sorry about that. And that would be our final answer. And that is the area of our bigger hexagon. And so there you go. There's the lesson on area and perimeter and area of similar figures. The main concept, and we'll just go back to it quickly here, the main concept is this theorem here, that if the ratio of their side lengths is, let me just use this fun pen, and I'll do it like this. If the ratio of their side lengths, oh, that goes off the screen, but the ratio of their side lengths is a to b, the ratio of their area is going to be a squared to b squared. And when we get to chapter 12, we talk about their volume, they'll have the similar idea. So thank you very much.